Integrated 3 10.3.1 lecture. How many successful outcomes are there using the binomial probability model? So it says in a previous course, so last year, I think you guys skipped this, sorry. You might have learned about different ways to count all the possible outcomes of a probabilistic situation. So we had a math notes box about this. There's combinations where those work for situations where the order doesn't matter and results are not repeated. So we talked about this in class once. I was saying combinations are kind of like when I'm picking teams for your study teams, the combination of, I'll just use fake names, Johnny, Sam, Jane, and Harry it doesn't matter what order I pick them in, they're still in the same team. So the order wouldn't matter. But permutations are kind of like combinations, but the order matters. Permutations would be, an example of permutation would be maybe like if I have to make a 4-digit passcode, 1, 2, 3, 4 would be a different passcode than 4, 3, 2, 1. So even though I've picked all the same items, it matters what order they're in. So here's combinations and permutations. There's little formulas for each of those, and there is a math notes box in your book about those, so you can look for that. We're going to use combinations because that's what we're dealing with in this lesson. And then tree diagrams, I'm sure you've seen tree diagrams before. You can use those when the order matters and when results can be repeated. So in situations that do not fit these categories exactly, you used other methods such as rearranging letters or breaking counting problems into subproblems. Today you'll look at another use for combinations. Combinations is this one, where the order doesn't matter. We're going to be counting the number of successes in repeated attempts. So when I think of this, I always think of just coin tossing problems where you toss the coins and it can either be heads or, there's only two ways it can go. It's either heads or tails. This problem right here is a little bit different than the coin tossing problem. So let's read this. It says, Carrie is the top batter on her softball team. Carrie has a batting average of 400, which means she gets a hit 40% of the times she's at bat. So that means she doesn't get a hit 60% of the time she's up at bat. Carrie comes up to bat 4 times in a game. Let H represent a hit and M represents not a hit or a miss. For example, hit, hit, miss, miss, HHMM represents a game in which Carrie gets hits on her first and second times at bat and then does not get hits on her third and fourth times at bat. Make a tree diagram to list all the possible outcomes Carrie could have after 4 times at bat. So I started making my tree diagram, and I don't know if you guys have made tree diagrams before, but if you're not careful, it gets a little out of hand and it gets a little messy. But it would look kind of like this: hit, miss. This is her first time at bat, and there's probabilities here. The hit was her batting average was 400, so it's 0.4 is her probability of getting the hit, but 0.6 is the probability of missing. So this is the first time at bat. This would be the second time at bat. So like here she got a hit and then she got a second hit, or here she got a hit and then she got a miss. Or if she got a miss on the first bat, she can get a hit or a miss on the second bat. I hope this makes, I think you've seen these before. Okay, so here's our tree diagram. These are the 1, 2, 3, 4 times at bat, or the 4 trials. I can represent this situation if she First time at bat, she gets a hit, and then the second time she gets a hit, and the third time she gets a hit, and the fourth time she gets a hit. That would be hit, 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 hit. And then this second part, hit, 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 miss. Hit, 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 miss. See what I'm saying? So I was going to write all these out on the side, and I realized it would get really messy and confusing, so I'm just going to use what the answer key has. This answer key, this is the same exact thing that I just showed you that I wrote, but it's a little neater because they are able to line it up a little nicer. Okay, first at bat, second, third, fourth. So we're going to be referring to this and answering the questions. So if you have your book open, you can read letter B. It says, Carrie's dad buys her an ice cream cone if she gets exactly 2 hits in a game. Carrie prefers pizza over ice cream, however, and she has convinced her dad that if she gets 3 or 4 hits in a game, he can forget about ice cream. He can buy the whole team pizza instead. How many of the different possible game outcomes result in Carrie earning an ice cream cone? Well, remember, the ice cream cone is only if she gets exactly 2 hits. So you can just go through here and find, like, in this one, she got 4 hits, 3 hits, 3 hits here. So they actually have little stars by them in the answer key. These are all the ones that have exactly 2 hits, and exactly 2 hits is what gets her an ice cream. And then it says there's 6 of these results. I guess that answered letter B. It says how many of the different possible game outcomes result in Carrie earning an ice cream, and we'll just say 6 because 6 of these have exactly 2 hits. Letter C says the number of ways that Carrie can get exactly 2 hits can be represented by the combination of 4 things taken 2 at a time. How do the 4 and 2 relate in this situation? So they just told us that I can represent Carrie getting exactly 2 hits by this, the combination of 4 things taken 2 at a time. And then it's asking me, how do the 4 and 2 relate to the situation? Well, 4 is the number of attempts at bat. You know, there's like 1, 2, 3, 4 times she gets to try. And 2 is the time 2 is the number of times she's actually getting a hit. So 4 things taken 2 at a time. And then letter D says, are each of the possible game outcomes equally likely? Well, that was fun. I went ahead and, these are the probabilities. I don't know if you remember this from other classes or maybe earlier if we talked about this. You multiply these together. 0.4 times 0.4 times 0.4 times 0.4. That actually, I did that math. It was 0.0256. But then you can see it changes. 0.4 times 0.4 times 0.4 times 0.6. Well, I did that math too on my calculator, and it was 0.0384. They're all different. This one is, I was thinking this one would be the most likely because her probability of missing is 0.6. These are all 0.6s. And that turned out to be 0.1296. So the answer to their question is no, the game results are not equally likely. And then 130, where are we? We're on letter E. I'll just read it right here. What is the probability that Carrie earns an ice cream cone after a game? Well, remember there was 6 different ones of these where she can get an ice cream cone. So each of the 6 games with 2 hits has a probability of, these are for the 2 hits and these are for the 2 misses, if that makes sense. So the probability of her getting an ice cream cone is just 6 times this probability, which is about 35%. So in other words, this, remember I told you I actually did the work. I did 0.4 times 0.4 times 0.6 times 0.6 right here, and it was this number, 0.0576, and if I multiply that by 6, I get about 0.3456, and that's about 35%. And then letter F says, in this problem, you modeled Carrie's situation with a binomial probability model. A binomial probability model can be used if there are 2 outcomes for each trial. You know, like your tree, it has just 2 branches, one of which is arbitrarily called a success. And it can also, you can use this binomial probability model if the probability of success is the same for each trial, like it's always 40% that she's going to get a hit and 60, so it's the same each trial. The trials are the at-bats. And the number of trials is fixed, so we need to know how many there's going to be. There's only 4 of them. And the trials are independent. These trials are independent because what she gets at her second bat doesn't know what she got at her first bat. Or in other words, the first bat is over. Like, it doesn't affect whether she gets a hit or miss on her second bat. It's not like, say, when you're pulling marbles out of a bowl or something, and maybe there's some black marbles and white marbles, and when you pull the white marble out, you don't put it back. That changes the probability of the second time you pull a marble out, because now there's less white ones in there. But this one that's called dependent, the marble thing I just said. But this is independent because it's just like coin flipping. Like, the coin doesn't know what you flipped last time. Like, every time you flip the coin, it's a new flip. It doesn't have anything to do with the previous flip. So in Carrie's situation, identify what a success is and what a trial is and how many trials there were. So a success was going to be a hit, and a trial is going to be each at bat. So there's 4 trials here. Okay, this is getting long, so we're going to do another problem, I think, but I will make a part 2.